So very good afternoon to all the students. In this session we are going to start a new topic on the mathematics of asymmetric key cryptography, right? So coming to the agenda, the mathematics of asymmetric key cryptography consists of various concepts such as the primes, primality testing, factorization, Chinese remainder theorem, quadratic congruence, and exponentiation and logarithm, right? So these are all the various topics that come under this mathematics of asymmetric key cryptography. So in this session we are going to discuss regarding these primes, right? So we'll discuss what a prime is and are there any algorithms to check whether a given number is prime or not, and are there any algorithms to identify the number of prime numbers that are less than or equal to some given number n. All these things we'll discuss in today's session, right? So before going to the mathematics of asymmetric key cryptography, let us recap what we have discussed regarding this mathematics of cryptography. So in mathematics of cryptography we started our discussion with the binary operations, where a binary operation is defined as an operator which takes two inputs and gives one output. So if you consider this plus, minus and multiplication operators, it takes two inputs from the integer set z and it results a single output c, which again comes under the category of z, which is nothing but a set of integers, right? So this division is not at all considered as a binary operation, as it is violating the definition that a binary operation takes two inputs and outputs single output. But here in the division it takes two inputs a and b and generates two outputs, that is quotient and remainder. That is the reason why we won't consider this division under the binary operation, right? So after that we have gone through the greatest common divisor of two positive integers. It is nothing but the largest integer that can divide both those integers, right? So we have seen some algorithms like Euclidean algorithm and extended Euclidean algorithm, which are used to find the greatest common divisor, right? So this Euclidean algorithm is used to find whether to find the GCD of two positive integers, right? So this is how we have seen the table form also. So if we want to find the GCD of 25 and 65, we take 25 and 65 like this, and we will shift this R2 to R1 and R to R2 like that. We have followed some method, right? We have seen some examples on this Euclidean algorithm also. Right. After this we have gone through one of the important concepts in the cryptography, that is the modular arithmetic, where we have seen the modular operator which gives only single output, and that means we are going to consider only the residue. Residue is nothing but the remainder, right? Reminders. So this particular modular operator, we will denote it as mod, right? We won't make use of any symbols here. In C programming, we will represent it with percentage symbol, but in modular arithmetic we will be considering this modular operator with the term mod, right? So it takes two inputs a and b and it gives only one output, which is the remainder of this a by b. And remember that R is always non-negative. It cannot be negative. Reminders cannot be negative, right? So after that we have seen the set of residues, which is denoted by Zn, right? The set of least residues modulo n, which is denoted by Zn. It consists of the integers which are less than n, where n is any positive integer. So if I consider z, for example z2 represents two integers that are less than 2, that is 0 and 1. Similarly z6 means it consists of the least residues starting from 0 and ending with n minus 1. Similarly z11 means 0 to 10. These all the things we have discussed. We are just having a recap of these things, right? And similarly congruence is an operator that is used to identify or to represent the equality symbol, right? For example, if I want to represent two equal numbers, for example 10 equal to 10, so in order to equate these two numbers, I am using a symbol called is equal to here. But in modular arithmetic, to represent the equality, we are going to use a special symbol which is called as the congruence operator, right? Like this we will represent. So, and 12 mod 10 is congruent to 22 mod 10, is congruent to 32 mod 10, like that. So all these result, for example, 12 mod 10 will result in 2, 22 mod 10 will result in 2, 32 mod 10 will result in 2. Therefore all these we can call them as congruent. They are congruent to each other. And this one we have discussed, right? And set of residues, so classes, residue classes we have discussed. So if I take a class 0, then this represents the numbers which give a remainder 0 when it is divided by n. So class 1 represents all the numbers from set Z which gives the remainder 1 when it is divided by n. Like that we can have number of classes. So if you consider all the least values, least positive values from these classes, we will get the least set of residues which is denoted by Zn. This also we have discussed in the earlier discussions, and these are the different properties we have in the modular arithmetic, right? So the first property says that a plus b mod n is equal to a mod n plus b mod n whole mod n. Similarly, the second property is on subtraction, which says that a minus b mod n is given by a mod n minus b mod n whole mod n. And the third property is on multiplication, which says that a into b mod n is equal to a mod n multiplied with b mod n whole mod n. So these are the three very simple properties we have regarding this modular arithmetic, right? So I'm just rushing through these slides. Why? Because these are all the topics which we have already discussed in previous sessions, right? So these are the various properties we have. And coming to the inverses, this plays very important role in the cryptography, right? So we have two types of inverses. One is the additive inverse and the second one is the multiplicative inverse. So the additive inverse is the inverse which is defined with respect to the addition operation, and the multiplicative inverse is defined with respect to the multiplication operation, right? Both of them are important. So how do you define an additive inverse? Means in Zn, which is nothing but the set of least residues of n, where n is some integer value, two integers a and b are said to be additive inverse to each other if they satisfy this particular property, that is a plus b is congruent to 0 mod n. In simpler terms, we can also write it as a plus b mod n should result in 0. Then we say that a and b are called as additive inverses to each other, right? And for example, if I take Z10, so what are the values that are present in Z10? These are the integer values which are less than 10. So it starts with 0, 1, 2 and so on up to 9. So how many additive inverses are there? Out of these, all these things, how many additive inverses are there? Means we can simply say that 0 is having an additive inverse. For example, additive means you have to consider only the addition operation. 0 plus 0 mod 10. What is the value? It is 0. Similarly, if I take this set 1 plus 9 mod 10, which is equal to 10 mod 10, which is equal to 0. Like that, 2 plus 8 mod 10 is 0, 3 plus 7 mod 10 is 0, 4 plus 6 mod 10 is 0, 5 plus 5 mod 10 is 0. So every number inside this Z10 are having the additive inverses. So what is the additive inverse of 1? It is 9. What is the additive inverse of 2? It is 8. Additive inverse of 3 is 7, additive inverse of 4 is 6, and additive inverse of 5 is 5. So if somebody asks in the reverse order, what is the additive inverse of 6? We can say that it is 4, nothing more than that, right? And coming to the multiplicative inverse, which plays very important role, right? It has very important role in the cryptography. in Zn, two numbers a and b are multiplicative inverses of each other if they satisfy this particular formula, that is a into b. Why? Because this is a multiplicative inverse. That is the reason why we are considering the multiplication operation, right? So a into b is congruent to 1 mod n. In simpler form we can write it as a multiplied b mod n is equal to 1, right? And remember that in order to identify whether a number is having a multiplicative inverse or not, first of all you have to find the GCD of those two numbers. If the GCD of those two numbers is equal to 1, then you can identify, you can just check that that particular number is having the multiplicative inverse. So if the GCD of that two numbers is not equal to 1, then two numbers means, for example, if I want to find whether a is having the inverse or not. So for that what you have to do, first of all the step 1 you should identify you should calculate the GCD of a and n. So if the GCD of a and n, where n is nothing but the number, right, z10, so n becomes 10, z6, n becomes 6. So if the GCD of a and n is equal to 1, then we can say that a is having a multiplicative inverse. What is the value of that multiplicative inverse is a different case, but in order to check whether a number is having the multiplicative inverse, GCD plays very important role. If GCD of a and n is equal to 1, then the multiplicative inverse exists, right? So in modular arithmetic, an integer may or may not have multiplicative inverse. This is important, right? So in Zn we have some set of numbers. All the numbers may not have the multiplicative inverses, right? So for example, what is the multiplicative inverse of 8 in Z10? So for this purpose, in order to identify whether 8 is having the multiplicative inverse or not, you should find the value of GCD of 10 comma 8, where 10 is n and 8 is a. So GCD of 10 and 8 is 2, it is not equal to 1. Therefore this number 8 does not have the multiplicative inverse. This is a very shortcut to identify whether a number is having the multiplicative inverse or not, right? Similarly, for example, if we want to find the multiplicative inverses in Z10, I know that Z10 consists of elements from 0, 1, 2, 3 and so on up to 9. In order to identify whether 0, 1 is having the multiplicative inverse or not, you just find GCD of 10 comma 1, it is 1. Therefore the multiplicative inverse exists. So what is the multiplicative inverse means? You identify a number b such that a into b mod n is equal to 1. So if I take a is equal to 1, you should identify b such that if you multiply those two numbers and modulo operate with n, you should get the remainder as 1. So if I take 1 into 1 mod n means 10 here. 10, what is the result? It is 1. Therefore the multiplicative inverse of 1 is 1. For example, if I want to find the multiplicative inverse of 3, so what should I do? 3 into b mod 10 is equal to 1. This is the relation it should be satisfied. So you need to identify a number b such that this relation is satisfied. So let us take. So 3 into 0 mod 10. What is the value? 3 into 0 mod 10. It is 0 mod 10. What is the value? 0, right? And you take the next number. 3 into 1 mod 10. 3 mod 10. What is the value?
You are now on.
It is 3, right? And you take the next number. 3 into 2 mod 10. 6 mod 10. It is 6. Next, 3 into 3. 9 mod 10. It is 9. Next, 3 into 4, 12 mod 10, it is 2. 3 into 5, 15 mod 10, it is 5. 3 into 6, 18 mod 10, it is 8. 3 into 7, 21. 21 mod 10 is 1. Therefore 3 and 7 are inverses to each other, and similarly 9 and 9, these are the inverses to each other. So 9 into 9 is 81, 81 mod 10 is 1. So this is how we find the multiplicative inverses, right? So is it clear?
Yes, sir.
Yes, sir.
So that's all about the recap of what we have discussed in the mathematics of the cryptography regarding these Zn and additive inverses, binary operations, all these things we have discussed. Now we are entering into the topic of our interest for today's session, that is the primes. So this is a topic that comes under mathematics of asymmetric key cryptography. Right. So this is the first topic. So what do you mean by a prime number? You all know very well about this prime number. What do you mean by prime? So a number which is having 1 and itself as the factors, then those numbers are called as prime numbers. So if you take the positive numbers, so these are the topics we are going to discuss under this prime. So asymmetric key cryptography uses primes extensively. That is the reason why we are discussing this primes concept. So we'll discuss what the definition of prime is, what is the cardinality of the primes, and how do you check the primeness of a given number, what are these Euler's 5 function, Fermat's little theorem, and Eulers Theorem. These are the topics which we are going to discuss under these primes, right? So if you take the set of positive integers, the set of positive integers is divided into 3 groups. The first one is a single number 1. Why? Because it is having exactly one divisor. Am I right or not? And the second category is the primes, which has exactly 2 divisors. Those 2 divisors are 1 and itself. So if a number is having the divisors as 1 and itself, those numbers we call them as the prime numbers. And the third category is the composite numbers. So if you have more than 2 divisors, 1 and itself are obviously the divisors. But other than this 1 and itself, it may have more number of divisors. Such type of numbers are the positive integers. We put it under the category of composite numbers, right? So this is how the positive integers are divided into 3 groups. The 1 is a single group, primes are another group which consists of numbers that are having the divisors as 1 and itself, and the third category is the composite numbers which are having more than 2 divisors. Clear?
Yes, sir.
Right. So if you look at some examples on these primes, what is the smallest prime we have? So all the numbers are divided into 3 categories: 1, primes, and composite, right? So what is the least number that we have under this prime category? That is 2. So you people may be thinking that it is 1, right? But 1 is neither prime nor composite. We won't put it into these groups. It is a separate group, right? So the least prime number or the smallest prime number is 2. Why? Because 2 is having the factors or the divisors as 1 and itself. This is the least one, right? And list out all the primes that are less than 10. Right, we won't consider 1. So you should start with 2, 3, 4, 5, 6, 7, 8 and 9. Right, these are the numbers that are less than 10, excluding 1. So if you consider 2, we know that this is the smallest prime, therefore take it as granted. And if you take 3, 3 is having the factors as 1 and 3 itself, therefore this is also a prime number. And if you take 4, 4 is having the factors as 1, 2 and 4. Therefore, it is having more than 2 divisors. This is not a prime. If you consider 5, 5 is having the divisors as 1 and itself. Therefore, this is a prime. 6, it is having more than 2 divisors, not a prime. 7, it is having only 2 divisors, it is a prime. 8 is having more than 2 divisors, not a prime. 9 is having more than 2 divisors, not a prime. So if you take the set of numbers that are less than 10, we are having 4 primes. Am I right or not? So if you take the percentage, 4 out of 10, 4 are primes. So out of 100, how many are there? It is 40%, right? So 40% of numbers under 10 are primes, but this percentage will decrease as the range increases. For example, if you take 100, right, there is no need that there should consist of 40 prime numbers. The prime numbers that are less than 100 will be definitely less than 40, right? Similarly, according to this formula, if I take 1000 numbers, 40% of 1000 means 400. 400 primes are not at all possible, right? So it is always less than 40%. This is the something you have to understand. Clear?
Yes, sir.
Right. And coming to the cardinality of the primes. So once you know what a prime is, you are able to you have to identify how many primes are there. Can anybody tell me a simple question, answer to a simple question, that whether primes are finite or infinite?
Infinite, sir.
Infinite, right? Since positive numbers are infinite in number, the number of primes are also infinite in number, right? So that is nothing but the cardinality. Cardinality means the number of primes. We are going to identify how many primes are there, right? Let us see. As you told that we have infinite number of primes, but how do you identify a number of primes that are less than a given number, or is given by this formula, right? The number of primes is given by n divided by log n. What is this ln stands for? Is it base 10, base 2 or base e? So ln stands for base e, right? So the lowest range will be given by this formula, which stands n by L log of base n, and this is the cardinality symbol. Number of primes is equal to n by same one log n minus 1.08366. This is an approximation formula, right? Don't assume that this gives the exact number of primes less than this n, right? It is giving a range of primes, right, which is just an approximation, right? We'll see it with an example. So find the number of primes less than what is this one? 10 lakhs, right? So if I want to find the number of primes that are less than 10, what I should do? I should put it in the formula, cardinality formula. What is the lowest range formula? What is the lowest range formula? It is n by log n, right, is equal to 10 lakhs divided by log of 10 lakhs base e. So it will turn around 72,383. So out of 10 lakhs of numbers, positive integer numbers, the lowest integer is 72,383. And what is the upper value? This is the lower value. What is the upper value you have? What is the formula? N by log n minus 1.086 something, right? 08366. So if you substitute the n value here, 10 lakhs by log 10 lakhs minus 1.0 something, the upper value I will get it like this, 78.543, right? So this is the range of values, approximate range of values that are given by the formula, and that gives the primes may fall under this category, right, under these two ranges. So the actual number of primes that are less than 10 lakhs is 78,498, right? So is this number falling in between these lowest and highest values or not? So what is the lowest value? It is 72,383. What is the highest value? 78,543. But actual number of primes when we actually calculate is, we'll get it as 78,498. So it falls in under this range also. Clear?
Yes, sir.
Yes, sir. Yes, sir.
Right. No need to remember this formula, but you just have an idea that we can identify or we can calculate the number of primes that are less than a given number by using that formula. You should know, you should have an idea that there is a formula that exists to find the range of numbers that can fall under this maximum and minimum value, right? And the next topic which we are going to discuss is checking for primeness, right? This we can also call it as primality testing. We'll again discuss this primality testing in the next topic also. This is called as primality testing or checking for primeness. So the name itself is giving some idea that we are going to test the primeness, or we are going to check the primeness. So if a number n is given, you have to check whether this given number n is prime or composite, right? So the maximum number of digits or the positive integers, they fall either in prime or composite. So you should identify whether this n is prime or composite. That is called as the primality testing or checking for primeness. So there exists a very simple but not accurate. It is not accurate. Remember that it is a simple method, but it is not accurate method. But still we are going to use this method to check whether a given number is prime or not. That is called as the square root method, or we can also call it as the divisibility method also. We can call it as a divisibility algorithm, right? So we'll see what this divisibility algorithm is saying. Given a number n, in order to identify whether this n is prime or not, the first step what you have to do is, you have to identify the square root of n, right? You have to, what is the first step you have to do? Please respond. What is the first step you have to do?
Identifying the square root of n.
Square root of n, and that too you have to take the floor value. Don't take the seal value. Floor means lowest value, right? And for this number, you have to list out all the primes that are less than this square root of n. Once you are done with step 1, you have to go to step 2. Step 2 says that you have to divide this square root of n with all the primes from this set. If any of the number is exactly dividing this square root of n, then this n is not prime. And within this set of numbers, if all the numbers are not dividing the square root of n, then we say that n is a prime. Very simple test, right? As I told that this is the most inefficient one, but it is a very good start. It gives us some good idea on how to check the primeness. Clear? Let us see with the examples. Is 97 a prime or not? So what is the value of n here?
Ninety-seven, sir.
97.
Sir.
So what is step 1 in divisibility algorithm? You have to identify square root of n. So square root of 97. What is square root of 97? As I told that you need to take the floor of square root of 97. What is square root of 97? It is 9, right? 9 9s are 81. Is it right or not?
Yes, sir.
After
Yes,
this, you have to list out all the prime numbers that are less than floor of square root of 97, which is nothing but 9. So what are the numbers that are what are the primes that are less than 9? It is 2, 3, 5 and 7, right? Clear?
Yes, sir.
Now you check
Yes, sir.
whether this any of these numbers is divisible, is dividing this 9 or not. So 9 by 2, is it divisible or not? 9 by 2?
No, sir.
No.
No, sir.
Sorry, not 9, right? We have to check whether n is divisible with these numbers or not. Right. So now tell me, 97 by 2, is it divisible or not?
No, sir.
No.
No,
Next,
sir.
97 by 3, divisible or not? No.
No,
97
sir.
by 5?
97 by 5.
No.
No, sir.
97 by 7?
97
No.
by 7. No.
Right. So all the list of primes that are less than floor or square root of 97 is not dividing this 97. If it is not divisible, then 97 is a prime. Don't get confused. If it is not divisible by any of the primes that are less than square root of n, then n is a prime number. If any of the number is divisible, is dividing this n, then it is a composite number, right? So let us see what happens in 301. What is square root of 301? 17. So that is step 1. In step 2, you have to list out all the primes that are less than 17. So there are 2, 3, 5, 7, 11, 13 and 17. Now you start dividing this 301 by 2, right? Not divisible. 301 by 3, not divisible. 301 by 5, not divisible. 301 by 7, right? 7 4s are 28, 7 3s are 21. Therefore it is divisible. Therefore this 301 is divisible by one prime, that is 7, which is less than square root of 301, right? So this 301 is not a prime. Clear?
Yes, sir.
Right. It's a very simple test which we call it as the divisibility algorithm, and as I told that this is not the standardized algorithm, or this is not a standardized algorithm, right? Clear?
Yes, sir.
Yes, sir.
Next we are going to discuss one more important topic, that is the finding number of primes. The previous one what we have discussed is it is to check whether the given number is prime or not. Now this concept is finding the number of primes that are less than some given number n. How many number of primes are there? That is what we are going to discuss, right? So we have different methods here, different algorithms are there. The first one is sieve of Eratosthenes, and the second one is Euler's phi function. We can also call it as Euler's totient function also, right? And Fermat's theorem, and finally we have Euler's theorem. Let us see what is this sieve of Eratosthenes. So it is one of the most efficient way to find all the primes that are smaller than n. For example, if somebody asked you to find the number of primes, or to find the primes that are less than 50. So what you will do is you will put a table like this, and you list out all the numbers starting from 2 up to the number which the user has asked. So let us check this one. I am asking about this 50, right? So from 2 to 50, I put a table like this, 2, 3, 4, 5 and so on up to 10, like this I will try, right? So you have to check each and every number. 2 is prime or not? S prime. 3 is prime or not? S prime. 4 is prime or not? No, this is not prime. 5 is prime or not? S. 6 is prime or not? No. 7 is prime or not? Like that you have to check each and every number starting from 2 and ending with 50. So finally you will end up with a table which consists of numbers which are not primes and which are primes. So how many primes are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So the number of primes that are less than 50 are 15. So this is it's not that much simple method, right? It is something like we can call it as a rot method, where you have to do lot of computations on it. But remember that you can also implement this by using the C programming or C++. You can simply write a simple program. You can write a simple program and you can find whether you can find all the primes that are less than a given number. Very simple while programming. But if you do this using this pen and paper method, it will take a lot of time, right? Is it clear? So the sieve of Eratosthenes is used to find the prime numbers that are smaller than a given number n. But remember that the disadvantage with this particular method is this is efficient only when you have n value smaller than 10 million, right? So 10 million means 10 power 7, I think. If you have a number larger than this 10 power 7, right, or 1 crore, then this method is inefficient. Is it clear?
Yes, sir.
Is it simple method or not?
Sir.
No, sir.
Right. So it is simple whenever the n value is less than 10 million. Otherwise it will be very complex, right? And the second method which we are going to discuss regarding this finding the number of primes that are less than n is the Euler's phi function. Euler's phi function. As I told that this is also called as Euler's totient function, which is denoted by phi. The notation is also important. So Euler's phi function, the name itself is saying that it is phi. Therefore phi of n is nothing but it is Euler's totient function or Euler's phi function. This Euler's phi function is used to find the number of primes less than n. Clear? We'll see what this Euler's phi function is. We have 4 different formulas here. So Euler's phi function denoted by phi of n, which is sometimes called as Euler's totient function. It plays very important role in the cryptography. Why it plays important role means it is the function which is used to identify or to list out the number of integers that are both less than or smaller than n and relatively prime to n. So it simply gives the prime numbers, list of prime numbers. So the first rule of this Euler phi function is phi of 1 is equal to 0. The second one is phi of p is equal to p minus 1. Remember, whenever we are discussing the mathematics related to the cryptography, when you come across this p, it is called as a prime number, right? Other than this p, if you take any m or n or x or a, something like that, it is a composite number. It is just a notation that you should keep it in mind, right? So p always stands for the prime number. So phi of p is equal to p minus 1, where p is a prime. Similarly, the third formula is phi of m into n, m product n, is equal to phi of m multiplied with phi of n, where m and n are relatively prime, right? Relatively prime means these both numbers should have the GCD as 1. That means their common divisor is not more than 1. Clear? Is it clear up to this point? We'll see with a few examples, then it will be very clear for you. And the fourth formula, last formula, is phi of p power e. As I told that p always stands for prime, right? So p power some number that is given by p power e minus p power e minus 1. This is also if p is prime. So based upon these four formulas, we are going to find out the number of primes that are less than n. Clear?
Yes, sir.
Yes, sir.
Now,
Yes, sir.
another important point we should remember is we can combine the above four rules. You can mix the third rule and the fourth rule, or you can mix the second rule and the first rule, like the second rule and the fourth rule. Like that, you can mix the rules to frame your own phi function. That is not a big issue, right? So let us take some examples. I want to find the number of integers or the number of primes that are less than 13. So what is the value of n here? It is 13. Am I right or not? If I want to find the number of primes that are less than 13, I can go for the Euler's quotient function. So I should find phi of 13. So what is this 13? Is it prime or composite?
Prime, sir.
It is prime, right? So if p is prime, phi of p is equal to, given by the formula, p minus 1. Am I right or not? So here p value is 13. So phi of p is equal to p minus 1. So that is 13 minus 1, that is 12. Which rule is it? Is it rule 1, rule 2, rule 3, or rule 4?
You are now unmuted.
Rule 2, sir.
Rule 2, right? So according to rule 2, phi of p is equal to p minus 1. So if you list out the numbers that are less than 13, right, we will get these numbers, right? So what is the value of phi of 10? What is the value of phi of 10? So how can I write it? So 10 is not a prime number, right? So I should find the factors for this one. So 10 can be written as 2 into 5. Am I right or not? So phi of 10 can be written as phi of 2 into phi of 5. Clear? So which rule is this one?
Yes, sir.
Rule 3, sir.
Rule 3. So according to this, 2 is a prime number, therefore it is 2 minus 1 into 5 is also a prime number, therefore it is 5 minus 1. Therefore it becomes 1 into 4, that is 4. Right? Clear?
Yes, sir.
Yes, sir.
And remember, whenever you find the factors of this 10, this 2 and 5 are primes, are relatively prime to each other. Then only you can apply this formula, right? Let us see. So what is the value of phi of 240? You cannot identify, right? This is not a prime number, it is guaranteed. And what you have to do is, you have to divide this 240 into the powers of the relatively primes. So 240 can be written as 2 power 4 into 3 power 1 into 5 power 1. Where 2, 3 and 5 are, what are these 2, 3 and 5?
Prime number.
Primes, right? So this formula has to be applied. Fourth rule. So according to fourth rule, it is 2 power 4 can be written as, it is phi of 240 is equal to 2 power 4 minus 2 power 3, that is 16 minus 8 into 3 power 1 minus 3 power 0, that is 3 minus 1 into 5 power 1 minus 5 power 0, that is 5 minus 1. So if you multiply this, I will get it as 64. Is it clear?
Yes, sir.
Yes, sir.
Right. And what about this 49? Phi of 49. So if I apply the formula like this, it is 7 square, right? So I cannot take this one, 7 pi of 7 into phi of 7. This is not applicable. Why? Because as I told that when you want to divide this into two factors, these two factors should be relatively prime to each other. So this particular formula is not applicable. I may be thinking that 7 is prime number and here 7 is prime number, therefore 7 minus 1, 6 into 6 is equal to 36. This is not true, right? So you cannot apply this second rule. You have to apply the fourth rule, which says that 7 square, right, phi of 49 is equal to 7 square. So this is in the form of 2 p power e. So it is given by p power e minus p power e minus 1, that is 7 square minus 7 power 1, that is 49 minus 7, that is 42, right? So this important thing you should remember, that when you factorize a given number, those two values which you get should be co-primes to each other or relatively prime to each other, right? Clear?
Yes, sir.
So the primary purpose of this Euler phi function is it is used to find the number of integers that are both smaller than n and relatively prime to n. This is very important, right? So this Euler function is used to find the numbers that are less than n and as well as relatively prime to n. Clear?
Yes, sir.
Right. So it is also used to find the Z14 star. What is Z14 star? This is the set of numbers which are having multiplicative inverses less than 14, right? So if I want to find the number of elements inside the G14 star multiplicative inverses, I can easily find out this one, right, by making use of Euler's function, phi function, that is phi of 14 is equal to phi of 7 into phi of 2, that is 6 into 1, 6. So if you find the number of elements that are present in the Z14 star, I will get only 6 numbers, that is 1, 3, 5, 9, 11 and 13, right. So this is another application of Euler's phi function where you can find the number of elements in the Zn star, where Zn star means, I know what this Zn is. It is the set of least residues of mod n. Zn star means set of least residues of modular operator n, and those are the elements which are having only multiplicative inverses. Right? Clear?
Yes, sir.
And the last two algorithms we have are the Fermat's little theorem, and the Fermat's little theorem is given by this formula, a power p minus 1 congruent 1 mod p, or the second version is a power p congruent a mod p. So can anybody what is the use of this Fermat's little theorem? What is the use of this Fermat's little theorem? The main purpose of this Fermat's little theorem is to find or to simplify the exponentiation values. We will see with an example, right? So find the result of 6 power 10 mod 11. Let us see what these formulas are saying, right? So a is any integer, and as I told that p is prime. So if I have a formula like a power p minus 1 congruent 1 mod p, this can be rewritten as this one, a power p minus 1 mod p is equal to 1, that's it. And this can be second version of Fermat's little theorem, can be written as a power p mod p is equal to a, simple thing, right? So let us see with an example how this is used, right? 6 power 10 mod 11. So it is very difficult to identify this value, right? You have to find the 6 power 10 and then you have to do these things, right? But if you carefully observe here that this particular given problem looks like a power p minus 1 mod p. Am I right or not?
Yes, sir.
Right. So here p is prime number, which is 11. So this is written as 6 power 10 mod 11. So according to Fermat's theorem 1, a power p minus 1 mod p is equal to, what is the value? What is the value? A power p minus 1 mod p is equal to 1. Right. So in order to simplify these exponentiation calculations with respect to the modular arithmetic, like 6 power 10 mod 10 means you have to find the 6 into 6 into 6 into like that 10, and then you have to divide it by 11, and whatever remainder you get, that should be given as the answer. But here the Fermat's little theorem, it is simplifying our exponentiation problem. If you carefully observe, this modular operator n should be a prime. Modular operator n should be a prime. And if you have the format like this, a power p minus 1, this a can be anything, right? This a can be an integer, any integer. For example, if I take 29 power 10 mod 11, this is also 1, nothing to do, right? Why? Because you should identify this particular 11, if it is prime, and if the entire given problem is in the formula of a power p minus 1 mod p, according to Fermat's little theorem, it is equal to 1. This is how we are going to simplify this exponentiation problems. Is it simple or not? Is it simplifying or not? Right. And this is about the first formula, where it is putting one restriction that p is prime and a is an integer, and the restriction is that p does not divide a. This is the restriction we have in Fermat's little theorem version 1. But in version 2, it is removing that particular condition. This condition is not there. It simply says that p is prime and a should be integer. That's it. So coming to this one, second example, find the result of 3 power 12 mod 11. Is 11 a prime or not?
Yes, sir.
Yes, right. So in order to convert this given sum into given problem into Fermat's little theorem, what I am doing is, can I write this 3 power 12 as 3 power 10 plus 2 mod 11 or not? I can convert it, right? So can I write it as 3 power 10 mod 11 into 3 square mod 11?
Yes, sir.
Right. What is 3 power 10 mod 11? According to Fermat's little theorem 1, a power p minus 1 mod p is equal to 1. Right. Into 3 square is 9 mod 11. So this becomes 9. So 1 into 9 is equal to 9. So this is how this Fermat's little theorem is very much helpful in simplifying the or finding the solutions for the exponentiations in a easier manner. Is it clear?
Yes, sir.
And this another application of this Fermat's theorem is the multiplicative inverses. Multiplicative inverses can be easily identified. In general, what is the method that we use for finding the multiplicative inverses? We have seen this one. So extended Euclidean algorithm. One of the application of extended Euclidean algorithm. Euclidean algorithm's application is to find the GCD. But extended Euclidean algorithm is to find the solution for the linear equations, and it is also used to find the multiplicative inverses. This particular point we have discussed it in the earlier sessions, right, while discussing the modular arithmetic. So one of the application of extended Euclidean algorithm is to find the multiplicative inverse. But without making use of extended Euclidean algorithm, you can identify the multiplicative inverses by making use of this Fermat's theorem. So according to this Fermat's theorem, we have a power minus 1 mod p is equal to a power p minus 2 mod p. So for example, if you take this 8 inverse mod 17, that means I want to find the inverse of 8 in modular operator 17. This is what the meaning of 8 inverse mod 17. Find the inverse of 8 in the modular arithmetic 17. So according to this formula, Fermat's theorem, I can simply write it as a power minus 1 mod p is equal to a power p minus 2 mod p, right. So here this is p, this is a, so I can write it as a power 17 minus 2 mod 17, that is equal to 8 power 15 mod 17. We will see how to simplify this 8 power 15 mod 17 in the later classes, but at present time you have simplified this one, right. Similarly, according to this one, 5 inverse mod 23 means you have to identify or you have to find the inverse of 5 under modular arithmetic 23. So there I can write it as 5 power p minus 2, that is 23 minus 2 mod 23, that is 5 power 21 mod 23. Like that you can find the multiplicative inverse of a given number by making use of this particular formula. Clear?
Yes, sir.
Yes, sir.
Right. So last 5 minutes. The last topic which we are going to discuss is the Euler's theorem. So the Euler's theorem can be called as a generalization algorithm for Fermats. Generalization for Fermat. So in Fermat we have some restriction that p should be prime and a is an integer and p should be divisible by a. All these restrictions are there. But in Euler's theorem it is giving a generalized thing, right. So here the modulus in the Fermat theorem is the prime, p remains the prime, same. The modulus in the Euler's theorem is an integer. This is the difference between the Fermat theorem and the Euler's theorem, right. So Fermat's theorem is exclusively defined on the prime numbers, right. But here we are not going to concentrate on the prime numbers. We are generalizing it. We are not defining, we are not restricting ourselves to the primes. So this Euler's theorem gives the formula where we are not taking the prime but we are taking it as an integer, right. Here also we are going to introduce two particular formulas. The first one is a of phi of n is equal to is congruent to 1 mod n. This can be simplified as a of phi of n mod n is equal to 1. What is phi of n here? Can anybody tell me? Just now we have seen what is phi of n. By looking at
to find the number of primes.
Yeah, what is the
Euler's
name?
phi function.
Euler's phi function or Euler's torsion
Euler's
function.
phi function.
Right. So it is used to find the numbers that are less than n and relatively prime to n. Right. And the second version of this Euler's theorem is a power k into phi of n plus 1 is congruent to a mod n, or simply we can write it as a power k into phi of n plus 1 mod n is equal to a. Right. Here you can observe the difference between the Fermat and the Euler. Fermat make use of p, prime number, modulo prime. But here this is a generalized thing of the Fermat. Euler's is a generalized thing of Fermat, where we are not putting restriction that n should be prime. It can be any number, any number. It can be prime or composite, anything, right? So this second version of this Euler's theorem, that is a power k into phi of n plus 1 congruent to a mod n, is exclusively used in the RSA crypto system. Very important thing. Clear?
Yes, sir.
Yes, sir.
So where we are going to use this Euler's theorem? What is the application of Fermat's theorem? The application of Fermat's theorem is to find the solutions of exponentiation modular arithmetic in a simpler fashion. That is what we have seen, right? So the Euler's theorem is a generalization of the Fermat's theorem. Therefore, the application of Euler's theorem remains the same. So it is used to find the solutions for the exponentiation problems in a simpler manner. But here there is no restriction that n should be prime. For example, if you want to find the result of 6 power 24 mod 35. Now see, is 35 a prime number or not?
No, sir.
No, right? We have 5, 7, other than 1 and 35, we have 5 and 7 as factors. Therefore, 35 is not a prime number. So, can we apply Fermat's theorem here? Can we apply Fermat's theorem? As I told that the Fermat's theorem is only applicable when this n is prime.
No, sir.
Right. Therefore, Fermat's theorem cannot be applied here. But what is the other choice I have? The other choice is you can go for the Euler's theorem. Euler's theorem says that what is the formula we have? A power phi of n is congruent to 1 mod n. So 6 power 25 mod 35 can be written as 6 power 5 35 phi of 35. So what is phi of 35? Now tell me. We apply the Euler torsion function. Is 35 prime or not?
No, sir.
No. So can we apply rule 2? No, right? So you have to split this 35 into two factors. 2 in what is that? 5 into 7. Am I right or not? Where 5 and 7 are relatively prime to each other. So phi of 5 into phi of 7. So phi of 5 prime. So 5 minus 1. This is rule 2 into phi of 7. 7 is prime. Therefore you apply rule 2. 7 minus 1. That is 4 into 6. That is equal to 24. So 6 power phi of 35 is nothing but 6 power 24. Am I right or not? Why? Because phi of 35 is equal to 24.
Yes, sir.
So phi of 35 mod 35 according to the Euler's formula it is 1. Clear?
Yes, sir.
So coming to 20 power 62 mod 77. Now can I write it as 20 power phi of 77? What is phi of 77? Can anybody tell me? Phi of 77.
60, sir.
This is 60. Let me check it out. So this is not prime, therefore it can be written as 7 into 11. So pi of 7 prime, that is 6 into phi of 11, this is prime, therefore 10, 60. Super. Right. So it is 2 power 60 mod 77 is equal to 1 according to Euler's theorem. Right. But here I can write like this: 20 power 60 plus 2 mod 77. This can be written as 20 power 60 mod 77 into 20 square mod 77. Right. I am splitting this. So according to the Euler's theorem, this is 1 into 20 square is 400. 400 mod 77. Right. 77 into I think 5 is 35, 385. So what is the remainder here? 400 mod 77 means 1 into 400 minus 385, it is 15. Therefore, I get it as 15. Is it clear?
Yes, sir.
Yes, sir.
Right. So this is how you can do. You can apply the second formula also. That is k is equal to 1. You take it as k is equal to 1, and 20 power 62 mod 77 can be written as 20 mod 77 into 20 power 577 plus 1 mod 77 mod 77. Like that, anything you will get the same value. Clear?
Yes, sir.
Yes, sir.
So other than this, finding the solution for the exponentiations in a simpler fashion, Euler's theorem can also be used to find the multiplicative inverse. What is the first method that we know to find the multiplicative inverse? What is the first method? Just now we have discussed. Extended Euclidean algorithm. Right? This was discussed in first unit. And now we have seen what is the other method for finding the multiplicative inverse?
Fermat's theorem, sir.
Fermat's theorem. And here we have the third method to find the multiplicative inverse, which is Euler's theorem. Right. These three techniques can be used to find the multiplicative inverses of a given number. Right. So Euler's theorem can be used to find the multiplicative inverses modulo a composite. Here is very important point. The difference between the Fermat's theorem and the Euler's theorem. What is the first difference I have seen? Fermat's theorem is restricted to prime numbers only. Right? Euler's theorem is generalized thing where we can apply it to n, where n is any integer. And coming to the multiplicative inverses, Fermat's theorem is used to find the multiplicative inverses modulo a prime. So the modulo number should be a prime here. Fermat's is always restricted on prime numbers. You should always consider the prime numbers. But Euler's theorem is generalized. It is somewhat relaxed. No prime numbers, nothing. You take any n, Euler's theorem works. So this particular Euler's theorem can be used to find the multiplicative inverses of composite numbers also. Clear? So and the formula that is given is a power minus 1 mod n is equal to a power phi of n minus 1 mod n. Let us see. So according to 8 power 8 inverse of mod 77. Now tell me, can we apply the Fermat's theorem? In order to check whether we can apply the Fermat's theorem or not, you have to check whether on which number it is modulo operating. So what is the number it is modulo operating? 77. And you have to check whether that number is prime or composite. 77 is prime or composite?
Composite, sir.
Composite.
Composite, sir.
So can we apply the Fermat's theorem on 77?
No, sir.
No, right? So this 77 is a composite number, therefore you have to go for the Euler's theorem only to find the inverse. So 8 inverse mod 77 can be given by the formula a power phi of n minus 1 mod n. Therefore it can be written as 8 power phi of 77 minus 1 mod 7. So what is phi of 77? It is 60. Therefore 60 minus 1, 59. 8 power 59 mod 77. So let us see how we can simplify this in the next coming sessions. That's a different case. Right. Now coming to the second example. We'll end up with this second example. 7 inverse mod 15. So now tell me, can we apply the Fermat's or Euler's theorem? What formula you have to apply? What theorem you have to apply? How can you decide?
Euler's.
Euler's, sir.
How you have decided?
15 is a composite number, sir.
Right. You have to check the modulo number. If the modulo number is prime, you can go for the Fermat. If the modulo number is composite, you can go for the Euler's theorem. So 15 is a composite number. Therefore, you cannot apply the Fermat's theorem. Therefore, the only option I have is the Euler's theorem. So 7 power phi of 15. What is phi of 15?
8, sir.
Super. Phi of 15 can be written as phi of 3 into 5, where 3 and 5 are prime numbers and relatively prime. So phi of 3 is 2 and phi of 5 is 4. 2 into 4, that is 8. So 8 minus 1, it is 7. 7 power 7 mod 15. This is how we are going to simplify. So the points you have to remember, the difference between the Fermat's theorem and the Euler's theorem is, Fermat's theorem is restricted to prime numbers. Euler's theorem is a generalized format for the Fermat's theorem only. So it can be applied to any number. And coming to the multiplicative inverses, Fermat's theorem is used to find the multiplicative inverse of a given number only when applied to modular operator on a prime number. And the Euler's theorem can be applied to find the inverse of a given number when you are applying it on the modular arithmetic of a composite number, right? But there are no restrictions for the extended Euclidean algorithm. It can be used to find the inverses of both the prime modularity or the composite modularity. This is the difference. Clear?
Yes, sir.
Right. So the last topic, generating primes. Only 2 slides are there. Generating primes, Mersenne primes and Fermat primes. So Mersenne is a scientist who has defined a formula to enumerate all the primes, right? So this is the formula that Mersenne has given. MP is equal to 2 power p minus 1. For example, Mersenne of 5 I want to find. So it is 2 power 5 minus 1, that is 31. M11, it is 2 power 11 minus 1, it is 2047. But the disadvantage of this Mersenne prime is, what is the use of this Mersenne number? It is just giving a formula to list out the primes, to list out the number of primes, right? So the disadvantage is the number that is generated by the Mersenne number may or may not be prime. The scientist thought that he is going to give a formula that always generate the primes, but once you come across this M11, it is 2047, it is not a prime, right? So it may end up, the Mersenne prime is ending up with either the prime or composite, right? Similarly, the Fermat also has developed a formula to find out all the primes. The Fermat prime is given by f of n is equal to 2 power n plus 1. So f of 0 is equal to 2 power 0, that is 2 power 1 plus 1, that is 2 plus 1, that is 3. F of 1 is equal to 2 power 1, that is 2 square, 4 plus 1, 5. F of 2 means 2 power 4 plus 1, 16 plus 1. Like that, it is keep on generating the numbers. But the disadvantage of this Fermat primes is also, it may end up in generating the prime or not a prime number, which is not acceptable, right? So because of this disadvantage, we are going into the next topic, which is primality testing. But we'll discuss this primality testing in the next session. So in today's session, we have gone through the mathematics of the asymmetric key cryptography, where we have started with the definition of primes, and then we have gone through the cardinality of primes, where we have given the formula for finding the minimum and maximum value of a given number, and then we have gone through checking of primeness using the divisibility method, divisibility algorithm, where you have to find the square root of n and list out all the prime numbers that are less than square root of n, and then you check whether at least one number is divisible by the n is divisible by at least one prime number from the given list. If it is divisible, then it is not prime. If it is not divisible, it is prime. So after that, we have gone through some of the Euler's phi function, which is used to find the number of primes, relative primes, which are less than n, and later we have gone through Fermat's little theorem and then Euler's theorem, and then we have ended up our discussion with the generating primes, where we have given 2 formulas like Mersenne primes and Fermat primes. So that's all for today's session. Thank you one and all for joining the session. We'll meet in the next session.